Everybody, so we've heard a lot about now about ears, and those poor of you that come from a different field, your head must be a little bit buzzing now. But what I'm going to tell you about is that very much of that we have presented are invasive studies, and you probably won't get allowed to do much of this stuff on carpets or pangolins or whatever you would like to measure hearing on. So I would like to outline a few ways that you can work in more in less invasive ways. It says non-invasive here. It's not completely true, as you will see, but it's we hope that it will be true at some time. So one of the methods I will introduce to you is what we've talked a lot about already, is the ABR, the way of measuring the auditory evoked potential or the auditory brainstem response. And we have done that quite a lot these last years. We have measured all animals we could lay our hands on, from lungfish to alligators and cormorants and so on, because this is a way that you can, a relatively non-invasive way to measure auditory activity and to measure those audiograms I have shown you a lot of up to now. And it does enable comparison between different species. I'm going to talk a little bit about psychophysics later, but it's evident that this method, where you don't have to train your lungfish or whatever, is a much faster way to measure the audiogram. So what you do when you measure ABR is that you have some electrodes that you insert either on the animal or in the animal, but very like, for example, subdermal electrodes. And what they measure is synchronous activity of neurons in the auditory pathway. And typically the onset responses of activity. And you can assign those in mammalian measurements. People actually assign those to different stations of the auditory pathway. So you can say that there's activity in the auditory nerve, in the cochlear nucleus, in the midbrain, and so on. The problem is that when you record this, you will also record something that is not ABR, and that would be, for example, microphonics, muscle potentials, or cochlear microphonics. So this is simply that your electrode acts as an antenna and picks up the sound signal you're sending out from your loudspeaker. This is muscle potential, so activity in the animal's muscles, which are much larger than the microvolts you're recording from the auditory system. So that's the drawback with these measurements, these ABR measurements, is that you need to have an animal that is not moving, at least with the technology we have today. With humans, you usually tell people to lay down flat on a couch or so on. You can't really do that to your lungfish, but you will generally have to sedate it or immobilize it. So what are these auditory evoked potentials? Yeah, when you stimulate an animal with sound, even a very brief transient, there continues to be activity in the auditory pathway up to half a second after the click or the transient was off. First at the lower stations, and then eventually in the cortex, and then there will be complicated memory systems and so on calculating on this. So you have a very long series of activity. That is very weak, as I said, so it's in the microvolt range. You can pick it up by skin electrodes in humans. You just put some electrodes in the skin, as we'll see in a moment, or in animals you need to have often some subdermal small needle electrodes that you insert just under the skin. And then you can measure activity in the cochlea, cochleography, which measures the activity of the hair cells. You can measure the auditory brainstem responses, which are the early responses, so up to 10-20 milliseconds after stimulation. But there continues to be activity, also up to 50 milliseconds. There are these responses, and up to 500 milliseconds, that would be these responses. people that work with animals haven't done very much out of the vague responses, but they tell you about cognitive functions related to sound that could be interesting enough. So yeah, isn't it sweet? So with babies, you don't use needle electrodes for obvious reasons. But you use some skin electrodes that you place, and you typically place them around the vortex. That doesn't seem right. It's not a vortex. What's it called? The vertex. Sorry, around the vertex, and you usually place one behind the ear, and then there might be a reference electrode on the chin or something, and then you pick up something, and here you see some peaks. A peak that corresponds to the cochlear nerve, a peak that is assigned to the cochlear nucleus, and a peak that's assigned to the lateral lemniscus. And this is done routinely in babies because you want to know at the onset, at the birth, whether they have normal hearing, or you should set in with hearing aids to get a normal speech development, right? So you can screen the hearing that way. And you usually place them and you do this differential recording between the mastoid behind here and the vertex up here. Ideally here, but most people don't allow you to shave the top of their heads for electrode placement. So you usually put it here instead. And then you have a ground electrode. And we pretty much do the same in animals. So this is what the ABR looks like. So when you do ABRs, you usually use a broadband signal that gives you good synchronization. That's one of the options. So if you fire a very short signal, you'll activate a lot of neurons at one time, and you'll get a strong summation of them. You can also use a tone burst. That way allows you to measure the response to different frequencies. And you can use a chirp, a short frequency sweep, which actually gives you the optimal synchronization, because you make one that is opposite to the direction of the traveling wave, and then you get a condensation of the response. But that's a technicality. And we have developed a fourth method that I won't really talk about. So if you do that, you can get these audiogram based on. This from the chinchilla is based on different peaks in the evoked response. So the characteristic is that you typically have these weak signals. You need to average a lot of time, and the electrode position is a little bit critical. So if it needs to be in the right spot, right? So if you move it, you won't see anything. So the signal should be short, and the problem is that the shorter the signal is, the more wideband it generally is. So there's a conflict between getting a precise frequency information and getting a good location of it. But the other thing is that, of course, this signal will be affected by a lot of things of the animal. You're sort of measuring the activity of the whole animal. So anesthetic, metabolic state, sleep stage, probably that's my pet theory, does affect the level of the ABR you get. Here's an example from the fish world. So here are studies on fish where you have a speaker, you have the fish in a tank, and calibrate the sound with a hydrophone here and record the ABR from it. And then you can see these results. This is from a shed with ultrasound stimulation, and was one of the first demonstrations of ultrasound sensitivity in fish. Here are some of our results. So this is the radiate slider that you saw before, and 3 needle electrodes inserted, one over the ear, that's this one, and then one on the top of the head, that's this one, and then the ground electrode here. And what you then measure is a response to sound that generates a nice sigmoidal curve from which you can calculate a threshold. So this is actually a very simple measurement. It's an easy and straightforward measurement. Here's our ABRs from geckos and anoles, and that allowed us to calculate quite accurately the audiogram of these animals. And imagine having to train an anole psychophysically, right? I would dare you to do it. So these measurements can be used for getting the general audiogram. It can be used for getting temporal resolution of hearing. It's been done in some birds. Directional hearing, or comparing hearing of individual under different conditions. The treatments like you saw our TTS experiments on the radiate slider before. So that's a very short on ABRs, and I know that Adam is going to talk about it later, because of course what we really would want to do would be to make this completely non-invasive. So the dream is to be able to have this in a device that you could put on the head of an animal and then get its hearing. And that is very much work in progress. Adam has got it to work underwater with porpoises, and he's going to tell you about that. So a tag that measures ABR on a freely moving porpoise. But imagine to be able to do it on a rhino, right? That would be the cool thing. So that's the ABR measurement. And now a little bit of psychophysics. So psychophysics is a behavioral measurement of animal sensitivity, and it is an accurate measurement of the relationship between physical parameters like frequency, sound level, sound direction, and the animal's perception of it. It's a way to quantify the animal's perception. And we measure the physical parameters, but you score the behavioral response, which is sort of a black box. The problem in psychophysics is that we don't know where the decisions are made, of course. Where the sensitivity exactly comes from, it's a property of the whole animal. And there are methods that deal with this, and I'll only just touch them here. So the fundamental thing in psychophysical method is that you need to have a behavior. And that behavior doesn't need necessarily to be trained. It could be that whenever you play a sound, the impala will wiggle its ears or turn around or something. If you can make a decent psychometric curve of that, you can use that to measure that animal's hearing. In turtles, the only behavioral audiogram that has been made was made because they had a turtle that had a tendency to make an eye blink when you played sound to it, and from that you got a very nice audiogram. I think they may have combined that with not hitting it on the shell when they do it with sound. But that's the other way, of course. You can train a response, you can condition a response to sound. And in the marine mammal world, this is well known that you train the animal so when it hears a tone, it'll get something. And apparently mammals like to do this kind of stuff. Mammals are like seals or sea lions are sort of engaged in doing these kinds of experiments. Then you can do different strategies. The idea is, in marine mammals at least, that you usually use positive reinforcement. We've had sort of a debate at home about positive and negative reinforcement. The trainers don't like that, but the thing that works strongest is, of course, always negative reinforcement. So in animals other than marine mammals. If you had a turtle or a goldfish or so on, you would typically use negative reinforcement. But of course, if the animal needs to be motivated to participate in the measurements, then negative reinforcement is not a good idea, right? It kills the motivation, obviously. So there's debate about that.
Jakob, what's an example of negative reinforcement for you?
Well, I mean, let's say you want to measure hearing in a turtle, and then you play some tones, and every time that you have the tone on, you hit them on the shell, right, or knock them on the shell, right. That's something. It's not really hurting the turtle, but it's evidently something it wouldn't like, right?
Right.
And that then after some time you will have a conditioned response to sounds that way. One thing they're using, for example, with ferrets is that when they're drinking and there's a tone on, there's a slight electrical pulse on the drinking spout.
Oh.
I mean, it's not that they get hurt, but it's just a little bit nasty, right? And that conditions them to sound. But I mean, there's no doubt that negative reinforcers are much stronger.
But then it's a conditioned response, so you knock them on the when you play the signal and you knock them on the shell,
Yeah.
what do they do? Do they blink? Do they?
Well, they will probably do a blink or maybe a slight retraction. I've never done these experiments, but in the literature.
And then at some point down the line, you can play them a tone with
Yeah, and they
shell,
do,
and you'll see them.
and that would be the condition. I mean, it's really Pavlovian classical conditioning, right? So you can do that. Yeah.
Just a technical question. A positive conditioning would be give the fish if
Give it a
dolphin
piece of
gives
fish.
a jump, right?
Yeah, a piece of fish or something it likes. I mean,
But if the dolphin does not do the jump, you say no, you didn't give the fish.
then it's just
That's a
not,
negative one.
then it's not just it's just not getting the fish. If you would, I mean, if you reward it for an error, you will have to work a very, very long time.
But if you're not rewarding, it's not a negative conditioning as well.
No,
No, it's not that just that it doesn't get anything. Oh, yeah, in birds, one of the typical way to do the negative reinforcement is to switch off the lights. So you switch off the lights briefly, and then that's a negative response. I mean, if the animal is really eager to work, then just the thing that it doesn't get anything will sort of be something that makes it learn. It's just not as strong as giving it an electrical shock.
I just want to ask, what is the reason for the negative response? Because I mean, if you're doing a study, I believe you would want to give like positive responses in order for the animals to be conditioned. You know, what's the point of giving that negative responses?
I think for learning to occur well, it should sort of be tied into what the animal is normally using that particular sound for. And if you think of a situation where sound is normally aversive, where sound is normally a predator signal, then it makes sense to do a negative reinforcement. If sound is normally something that is associated with food and so on, then it makes sense to do a positive reinforcement. So but I have had some debates with our good trainer in Magnus's trainer, because it's in the trainer world they don't believe in negative reinforcements anymore. But I think it must depend on the animal. Okay, I just need to get that away. Excuse me. So your aim when you're doing these measurements is to make a psychometric curve. All good psychophysics experiments generate a psychometric curve, which is the relation between the intensity of the stimulus and the response of the animal, right? So if you have a low intensity of the stimulus, you have zero corrects or whatever it is, and if you have a high intensity, you should have like 100%. So your aim is to do some kind of measurements that can generate this curve, and that is what the training does for you. And I'll just briefly mention two methods that you can do. I had actually wanted to do a demonstration of this, but we don't have any proper sound, so I don't think I will do that. But imagine that you want to measure the sensitivity of a tone. You present it a bit above what you think is the animal threshold, and you see what the animal is responding in which way, either by pushing a button or doing something, right? And here it says yes, yes. And then you reduce the intensity in steps, for example, in steps here of 60 dB, so halving the intensity, and you say the animal says yes, 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 no, at this level here. So then you know that you have crossed the threshold, right? So then you can do various things, but then a way to go would be to then start from the bottom, from a bit below this, and go up, 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 and the animal says this is far below the threshold we measured before. So the animal should say no, 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 yes. So you now have two determinations of the threshold, and in fact you can continue as long as you want. The accuracy you want. The longer you continue this, the better accuracy you will have. So then you make another staircase and another staircase from below and so on. And then you have identified the threshold. Yes?
Does the longer you do your presentations, does anticipation not come into play?
Yes, it does. And you can, there are various tricks about this. But that is a problem with this method, especially if you do this in regular time intervals. I would maybe advise that this is not so good. But generally, the problem in psychophysics is pretty much that the thresholds you get depend on the methods you use. So you will get different. Let's say that you had that you only measure staircases from below, or only measure staircases from above. You would get two different thresholds. Because here you know what to listen for, so to speak, and here you wouldn't really know what to listen for. So in this case, the threshold would typically be higher. This demonstration, I will skip that, but there's another very good method that you can use, and that's the method of constant stimuli. And there you present a randomized set of stimuli, stimulus parameters. So if it was, you want to measure the threshold to a certain frequency, you give all kinds of different levels of that at that frequency randomized. So here will come a high one, and then there will come a low one, and then one intermediate, and then maybe a high one again, and so on. And from that response, you get very good psychometric functions where you can calculate the thresholds. And you need to, that stimulation can be controlled from a computer, and you have fairly short, fairly small errors. You can't, as you said, you can't really have expectation here because everything is randomized. And from the whole set, you then identify a threshold. And this is just one frequency. So this is also, you can also see that this takes time, right? And typically people measure the audiogram of one seal in a month or so. So just doing one frequency takes a long time. One thing that is a problem in psychophysics is the thresholds definition, and we tend to think that thresholds are a sort of a fixed thing, but in reality they aren't, because if you have a subject that is very prone to guess whether the stimulus is on, which we take a very what's the opposite of conservative? A very liberal, a very liberal test animal that is supposed to, if it really can't hear whether the stimulus is, it still says yes. That such an animal would score as having a lower threshold than an animal that was very conservative and very cautious about saying yes, yes, I can hear it. It really wanted to be sure. And these tendencies to guess can sort of move the thresholds up and down by 10 dB. And that takes you into a sort of a complicated matter called signal detection theory that I won't go into, but you can actually manipulate people's and animals' criteria by different rewards and punishments. So if you punish an animal for making false alarms by saying yes if you play some catch trials when the sound is not on, you will make it more conservative, and hence the thresholds will appear higher. If you punish it for missing the detections, it'll go the other way, of course. So it will make more false alarms, and because you cannot, you either will do the one or the other. You cannot avoid going one way or the other. And that's also a natural thing. I mean, if you are a moth that is trying to detect bats, the predatory bats, you would rather make some false alarms than you would get eaten, right? If you want to mate with one from your own species, you would rather you would rather miss than make a false alarm. So these criteria can be manipulated, and you can do that by experiments. And Ole says that I'll take too far that I go into it now. So I'll stop here, I think. Okay.
So we run half an hour or so.
Typically, the sort of increments in terms of the the frequencies that you're playing back? So when you're trying to generate audiograms.
Oh, that depends a little bit on the animal, but I mean, we typically go in 100 Hz steps.
Okay.
To get a, but when we did the cormorant, for example, it was we covered less. It depends on how cumbersome it is.
We doubled the frequency.
Yeah, that was a frequency doubling. It depends a little bit on what you want to do.
I have another question.
Yeah.
So can you speak a little bit about the biases involved? Because if you're working in, say, captive animals, versus, where they're available to do these kind of tests, versus wild animals.
Yeah, in case you can hear me, I strongly recommend that, you did the video that I sent you on Dropbox, if you can download it.
I'll do that.
Quick, base introduction, if you want, and then mute myself, you can play it, and then
I will, Adam. We're just running a bit over time, so I'll do it just in a moment.
No worries at all. It's sometimes hard.
Yeah, okay. So Tess, once again.
The biases involved with doing this sort of work with captive animals or trying to attempt it with animals in the wild, and also in terms of sample sizes, like what's an adequate sample size and what's not. I was just wondering whether the practicalities of actually conducting this kind of work, and when people are reading the studies and trying to interpret what they mean in terms of impacts of noise or sensitivity to noise impacts, then what should we be looking out for? Sorry, those are about 5 questions.
I think it's a difficult question, also a bit because I don't do very much of the psychophysical work myself. I'm sure that there would be differences between wild-caught animals and animals that are used to be in captivity. And also in animals in captivity, there's usually, at least in the bigger mammals, there's usually some relationship with the trainer where they really want to, which can define whether they really want to do good or not, right?
So some of the question relates as well to ABR.
ABRs is easier. I mean, they we just sedate the animal and measure, right?
Right, but like you're limited by sample size, you're limited by the availability of animals.
Yeah, sure.
How do those things interplay so that you find validity in the data?
Well, I mean, as biologists, we usually say 5 because that's where you can do a viable man-Whitney test, right? It's sort of the magic number, but of course, the more you have, the more sure you are in the results. And there might be some variability. I think there are not as much variability in ABR measurements as there would be in a psychophysical experiment. But as you saw with, for example, our barking gecko data, there are some, right, depending on. You don't put the electrodes exactly the same way every time, and there could be difference in levels of anesthesia and so on.
And ethically, I mean, there's got a lot of training to do for the psychophysical, but for the ABR, it's sort of unanesthetic. Is it a case of short and sharp and get a good result, or is it a case of training animals over time and it's maybe ethically less impactful?
Yeah, I mean, the animals that you do ABR on, in our experience, they all revive again after the anesthesia. We have put a little needle in their skin, but they usually recover completely, so we can release them after a few hours.
Okay, so you catch them in the wild.
I mean, we did that with the barking geckos and released them again.
Right, so that's the sort of gold standard. Catch them from the wild, do the ABR, release them.
Yeah.
Rather than using, say, ones that are in, I don't know, like the aquarium or the zoo or whatever.
Well, I mean, we could do that, but we're rarely allowed to do that, of course, because there's an extra risk when you anesthetize them. But I mean, if we could get on some animals that were anesthetized for other purposes, we would do that too.
And how long does it take? How long does it have to be under? Say for a gecko, how long was it?
Couple of hours.
Pardon?
Couple of hours.
Couple of hours, and it's done.
And with the turtles or tortoises we're doing at the moment, it's very nice because we can measure them, and then we're giving them a combination drug which has an antidote, so we actually revive them straight after the experiment.
If I can just supplement, actually we've been doing this with seabirds quite a lot in Iceland and also in Finland. So in Alaska, where we, went out, caught them, they brought them back to a shed, and there anesthetized, had them there for half an hour or so, made all the audiograms, revived them again, put them out to the cliff edge, and saw them wandering around a little bit like this, and then taking off flying out. And we did that for about 10 animals each time, and it worked really well. So this is really a very, very powerful method.
Yeah. Did you put tagging tags on it?
Sorry, can I just ask, like in the tagging methods in the birds versus now the turtles is the combination drug, the iron sedation of the being, but with the birds, I presume we use gas? Or
No.
Also
Injection.
Oh, okay.
All the time. We started out with the ketamine
Okay, yeah.
But for the merlets, which are really endangered in Alaska, we had to use a different antidote, a different combination, and an antidote to revive and avoid security. But if you want the exact medication, I can give it to you later on.
Adam, where did you put the video?